Just a moment. It's creating some problem. I'm trying to share the material. তোমরা স্ক্রিনে কিছু দেখতে পাচ্ছ? হ্যালো, কেউ একজন আনমিউট করো তো।
Yes, ma'am. Yeah, we can see your screen.
Which one? The lecture material?
No, ma'am.
So several such screens, okay?
Yes, just Jamit screen.
I don't know what's happening.
ম্যাম আই গেস আপনি ওটা উইন্ডোটাকে শেয়ার করছেন, গোটা স্ক্রিনটাকে শেয়ার করুন, তাহলে হয়তো হয়ে যেতে পারে।
গোটা স্ক্রিনটাই তো এতদিন শেয়ার করতাম, সেটাতে তো আবার মেসেজ দিল যে উইল সি মিরর্স।
ম্যাম খালি শেয়ার দ্য
First
উইন্ডো করুন,
time,
দিয়ে পরে
first
পিপিটি
time I'm
ফাইলটাকে শেয়ার
facing
করুন।
this kind of problem.
ম্যাম শেয়ার উইন্ডো করে পিপিটিটাকে খালি শেয়ার করুন, তাহলে চলে আসবে।
না, এটা তো you are presenting to everyone. Okay, that's fine. What's happening? এরকম তো কখনো হয় না। কি বলছিলে?
প্রবলেম নেই, ওটা তো যদি আপনি পিপিটিটা খোলেন তাহলে আমরা পিপিটিটাই দেখবো।
শেয়ার না করলে কি করে দেখবে?
হ্যাঁ, শেয়ার করার পর বলছি।
শেয়ার করতে গেলেই তো several such screens চলে আসছে।
হ্যাঁ ঠিক আছে, ওটা
মানে
আসুক,
this
ওটা প্রবলেম
first
নেই।
time I am facing this problem. এতদিন ধরে গুগল মিটে ক্লাস নিচ্ছি। ইনফ্যাক্ট এই গুগল মিটটা একটু চেঞ্জও হয়েছে, এটার লেআউট টেআউট গুলো চেঞ্জ হয়ে গেছে।
না ওটা প্রবলেম নেই, আপনি স্ক্রিন শেয়ার করে পর তারপরে পিডিএফটা খুলুন, তাহলে আমরা সব দেখতে পাবো।
ও, তুমি বলছো ওই মাল্টিপল স্ক্রিনস এলে কোনো
হ্যাঁ
প্রবলেম
ওটা
নেই?
না, ওটা কোনো প্রবলেম নেই।
ওকে। Can you see the material?
ইয়েস ম্যাম।
যে জুম করতে হবে না ক্লিয়ারলি পড়া যাচ্ছে?
পড়া যাচ্ছে না।
পরে হয়তো জুম করতে হতে পারে। Okay. So linear control system, you know the name of the course is linear control system. So this is basically a program core, and these are the lecture tutorial breaking anyway. You don't have to bother about all these things. Syllabus, detailed syllabus is given here, and you will get the syllabus or this particular material in our website as well. So I'm not going through the syllabus, right? But these are the reference books. Nice, Nagrad Gopal, Puo, M. Gopal. Several books are there. Now, these things are of importance. Course outcomes. So you should learn and we should remember what are the course outcomes. I guess you know what is meant by course outcomes, COs. I guess you have come across this particular term, course outcomes. Yes or no? Hello?
Yes.
Yes ma'am.
Please respond.
Yes ma'am.
Mute your device whenever we will be requiring some sort of interactions. Please unmute your device one by one. Please try to interact. So the first course outcome is the students should be, after finishing the course, obviously after finishing the course, the students should be able to explain the configurations of control systems, the notion of stability, and related concepts on steady state and transient errors, disturbance rejection, insensitivity, and robustness. Right? So today we'll start from this part, that is notion of stability. Now the next CO2 is, after finishing the course, the students should be able to describe different control system components, interpret time responses of the systems, discuss about the absolute stability of a system using Routh-Hurwitz criterion. Third CO3, the students should be able to develop knowledge on block diagram reduction technique and signal flow graph. The student should be able to develop knowledge on closed loop frequency response of an LTI system. Next, CO4, the student should be able to design suitable proportional PI, that means proportional and integral, PD, proportional and derivative, and PID controllers, proportional, integral, and derivative controllers. Students should be able to examine the dynamic behavior and stability of an LTI system by constructing root locus, and the student should be able to ascertain the stability of a system using Nyquist stability criterion. And the last CO5, the students should be able to analyze an LTI system and synthesize controllers for the same using state space techniques. The students should be able to design suitable compensators using both frequency and time domain based techniques. Please go through the COPO mapping. And COs are very important because after finishing the course at the end of the semester, you'll be asked to provide course end feedback, right? So there you'll have to provide feedback on this COs. So linear control systems, this is the name of this particular course, and I'll be covering the second part of the course. So we'll start, this is module 1, or you can say the first chapter, chapter 1. So the chapter, in this chapter, will try to learn the concept of stability, algebraic criteria, and then Routh-Hurwitz stability criterion. So my email is given. I do have another email ID from which I'll send the meeting links. So you can note down the email ID, madhubonti.moitro @jadavpuruniversity.in. So at any point, if you have any confusion, any doubt, any query, feel free to interrupt me and feel free to ask. Okay. Now, since I used to teach this subject using chalk and board method, hence for online courses, I've prepared a handwritten note. I think you won't find much difficulty in, I guess it is legible. Is it legible?
Yes, ma'am.
Okay, so let's start. So the first chapter is on the concept of stability. So what is meant by stability of a system? Whenever we talk about stability, that means we are trying to find out whether a particular system, a given system, is stable or not, right? So first we'll have to discuss, or we'll have to know, we'll have to learn what is the definition of a system. Already you have started uh, a course, or you have done a course on system theory, right? So can you tell me uh, some formal definition of a system? How do we define a system? Anybody please unmute your
Ma'am,
device.
system is something which process on some input signal and gives some output signal, and system may be
Okay, there are I accept this particular definition. There are very many formal definitions of a system, right? In very many ways, we can define a system, but in this particular context, this definition is really very pertinent. So, unless you have any doubt, please mute your device. So, what is a system? If we give an acceptable input to the system, what is meant by input? Some command. That means we are asking that particular box. If I consider the system to be a box, so we are asking the box or the system to do some work. So for that, we are giving some input to the system, or we are giving some command to the system, and accordingly the system should be able to respond, right? So in accordance with the command given to the system. So in terms of signals, if the system is excited with some acceptable, what is meant by acceptable, that we'll discuss. So if the system is excited with some acceptable input, the system should be able to produce, should be able to generate an acceptable form of signal as its output, right? So that means a system directly connects the output to the input. So now in this context, we can start defining the just describing the stability of a system in this manner. In the earlier days, a system was considered to be an unstable one if, for an acceptable input, the system exhibited undamped oscillation at the output. Clear? So an acceptable input, that means a bounded input. Suppose the system is excited with a bounded input, but at the output we are getting some undamped oscillation, then the system initially was considered to be an unstable system, right? But this definition is not a very clear or formal definition, right? So a system will be considered to be a stable system if, for a certain acceptable form of input, the output response can follow the input signal or input command. So if that be the case, then in a very lucid manner, we say that the system is a stable one. Do I have to repeat? Do I have to repeat?
Yes, ma'am.
So suppose we have given an input to the system, where we have given a command to the system, and if the output of the system is such that the output response of the system can follow the input command, right? Then we say in a lucid manner that the system is a stable system, right? And on the other hand, again, we can discuss the notion of stability in this manner, that if we slightly change the input to the system, or if we slightly change the initial condition, or if we slightly change the parameters of a system, then for a stable system, the output should not deviate from the previous one by a large amount. Have you understood this?
Yes, ma'am.
That means the input or the initial condition or the system parameters. You understand what is meant by system parameters? You understand what is meant by system parameters?
Yes, ma'am.
Okay. So for slight changes in those, the output of the system should not change by a large amount. So the stability is a notion that describes whether the output can follow the input command, or whether the output that is for a stable system, and for an unstable system, what will happen to the output? The output will gradually deviate farther and farther from the input. That means the output will not be able to follow the input command, right? Now, just with this introduction, let's have a look at typical control problems, and we can classify typical control problems, into two groups. One is a regulatory kind of problem. The second one is a tracking kind of a problem. So this is the first group, regulatory kind of a problem, and the second class of problems are denoted as tracking kind of problem. So what is the difference between these two? In regulatory kind of a problem, we give a fixed input to the system, right? So let's take one example. If we consider one example, then I guess very easily we'll be able to understand what is meant by regulatory kind of a problem. So suppose we want to maintain the temperature of a room, say at 25 degrees centigrade, right? So what should be the input command to the system? The input command should be a reference temperature or set point value, which is equal to 25 degrees centigrade, right? And the controller inside the system will act in such a manner that the temperature, that means the output of the system, that is the actual temperature of the room, will be, say, X degree centigrade, right? So since we are designing a controller, and since we are discussing a stable kind of a system, then it's expected that if the input signal is fixed and it is 25 degrees centigrade, then the output temperature, or the actual temperature of the room, or the desired temperature of the room, should be equal to 25 degrees centigrade, right? So set point is fixed. The input command in this case is fixed. So this is basically the regulatory kind of a problem. And what is a tracking kind of a problem? In case of a tracking kind of problem, the input command may not be fixed, like the previous case. So suppose a missile control system. So often what is done, the trajectory the actual, what should be the desert trajectory of the system, that particular trajectory is embedded into the computer of the missile, and the trajectory is pre-specified or predetermined. Trajectory means the flight path of the missile, right? So it will change with time. The flight path will naturally change with time. And the control system should be designed in such a manner that the system, that the system or the missile control system, the output of the missile control system, or to be more precise, the output trajectory produced or generated by the missile control system should be able to follow the input trajectory which is embedded into the computer, right? So let's take a look of this particular figure. The first one is depicting, the first case is depicting the regulatory kind of a problem. So this is the fixed input, often we call it a reference input or set point. And if you consider the example of temperature control system, so let's assume that this line is depicting a constant temperature which is 25 degrees centigrade, right? And this is the output signal generated by the system, and initially the temperature will start either rising, or if the temperature of the room is higher than 25 degrees centigrade, then it will start decreasing. And finally, since a controller is acting, since we are discussing a control system, the output, after a while, the output temperature or the actual temperature of the system or system generated temperature will be exactly 25 degrees centigrade. And you can see that the output is converging after this point, after this time instant, the output is converging with the input. That means, yes, the system is exhibiting a response which can exactly follow the input command. Is it clear what I've said?
Yes, ma'am.
Yes, ma'am.
Okay. Now, in this case, okay, let's come back to this figure. Now, suppose the output response is not like this, but instead, can you follow the cursor?
Yes, ma'am.
Suppose the controller is not working, or suppose if the system is not stable, in that case, what can happen? The temperature can rise, and uh, instead of converging with the input command, it can overshoot the input command and it can go on increasing. That is a possibility, right? So we can conclude that in this particular case, the case that we have discussed just now, the output command or output response cannot follow the input command, isn't it? And the output is going on, or going on increasing farther and farther, right? So that is not really desirable. That is not really desirable. And in that particular case, the system will be said to be an unstable system, right? Even if the temperature, the output temperature is something like this, right? Then also the system will be treated as an unstable system. Why? Because the output response cannot follow the input command. Now, in case of a tracking kind of a problem, suppose this is the input trajectory, which is embedded, which is fed into the controller or the computer of the flight control system. This is the input trajectory, right? And it might so happen that initially the output trajectory is a bit different from the input trajectory, but the missile, the output trajectory will converge with the input trajectory after a while. That means, what is meant by that? The missile will be finally able to follow its flight path, right? So if that be the case, then yes, the system is stable. And if that is not the case, suppose the output trajectory is something like this, right? So that means it might result in a catastrophic situation, right? So the missile will hit some other target which is not actually the pre-specified target. So that will result in some catastrophic situation. Okay. Or if the output trajectory is something like this, that means not in accordance with the input trajectory, then again the system will be considered to be unstable one. Now the question is why we are so bothered about the stability of the system. That means why we are so bothered about the output response of the system, and why do we actually try to judging stability of a system means we try to, in a lucid manner, again in a lucid manner, we'll study the formal definitions. In a lucid manner, we'll actually trying to judge the fact that whether the output response of the system can follow the input command or not. So why that is required? That is required because the system has been designed. A system is always designed for to perform some task, to perform some activity, right? And if the system fails to do so, then what will happen? Will not be able to work with that particular system. You get my point? If the system fails to perform the task for which the system has been designed, then the system will be useless. Yes or no?
Yes.
Yes,
The
ma'am.
system
Yes, ma'am.
system will be useless, and so will not be able to work with that particular system, right? That's why whether the output of the system can follow the input given to the system or not, this particular question, the answer to this particular question is so very important. So let us take one simple example. Suppose in your class, suppose let's assume that the class is not a virtual one, it's a physical one. And suppose if I ask one of you, say, to lift a heavy load. So now you or one of the students, he or she is acting like a system. And the input command to the system is that the system will have to lift a heavy load. Now, God forbid, if the student is not doing well, if he's feverish, then what will happen? While he or she will be trying to lift the load, he or she might start trembling. That means undamped oscillation, sort of undamped oscillation. Or in the process, even it might so happen that he or she may collapse. That means the system will break down. System will break down. So the purpose of lifting the load will be defeated, right? And hence it's clear that we are not in a position, to work with that particular system. So far, is this clear?
Yes, ma'am.
Hence, what is the task of the control system designer or system designer? After you design a system, the first task of a control system designer, a control system engineer or system engineer is to find out whether the system is stable or not, right? Because as I said, if the system is not stable, then we'll not be in a position to work with that particular system. So if the system is stable, fine. If the system is not stable, then we'll have to, if we want to work with that particular system, then we'll have to make the system stable by some means. Otherwise, we won't be able to work with that particular system. It will be simply useless. You'll have to throw away the systems. Okay. So the first task is to judge the stability, to ascertain the stability of the system. If the system is stable, fine. If the system is not stable, then we'll have to make the system stable. And if the system is stable, or when we make the system stable, then we often judge the performance of the system, right? And it might so happen that a stable system is not performing in a Dejan manner. Try to recall the knowledge that you have gathered while studying system theory. Second order system, you have studied step response of a second order system? Yes or no?
Yes, ma'am.
Okay, fine. So we know that if the damping ratio is very small, the damping ratio is small, then what will happen? The system will take huge time to settle down. The settling time will increase. And moreover, before settling down, the system will exhibit several damped oscillations, isn't it? I'm
Yes, ma'am.
assuming an underdamped system. I'm assuming an underdamped system. So that is often not measurable. So the system is stable. Ultimately, it's settling down. So the system is stable, but the problem is the performance is not up to the mark. It's not satisfactory. So then, after making the system stable, or rather, after judging or ascertaining the fact that yes, the system is stable, we check the performance. If the performance is satisfactory, fine. If the performance is not satisfactory, then we can go for performance enhancement, right? But remember, the first task is to ascertain the stability of the system. Already I have explained this. The task of a system or control system engineer to work with a system or a plant in general, the first task is to ascertain the fact that the system is a stable one. If the system is not a stable one, then the primary job is to make the system a stable one. Once the system becomes a stable one, then only we can think about the performance analysis of the system, and if needed, we can go for performance enhancement. Right? So unless I read out, you don't have to go through the lines what of the material what I am presenting, because I am explaining since chalk and board are not available, so that's why I've prepared a detailed note. Everything you'll find in this particular note. So try to listen very carefully, try to understand what I am explaining, right? And while you'll go through this material, I'll give you the material, and while you'll go through this material, you'll find almost every word that I'm explaining or I'm uttering. And one more important thing that I must mention, the name of the course is Linear Control System. So from the name itself, it's clear that in this particular course, we'll learn associated tools which can be applied only for linear system, right? We'll not discuss nonlinear systems. Moreover, we'll focus on linear time invariant system or LTI system. Will not consider linear time varying system, will not consider nonlinear system as well. Our focus will be only linear time invariant systems. And linear systems, that means that a linear system always obeys the law of superposition as well as law of proportionality, isn't it?
Yes, ma'am.
That is the advantage of the linear system over non-linear system. So, general notion of stability. To understand the concept of stability in more details, let's take some example. The first example is, or the in this particular examples, we'll consider different types of surfaces, troughs, different types of surfaces on which we'll be resting a ball. So that is our system. Okay. So the first surface that we consider is like this. You can see the surface. This is the surface, and the ball is resting on this particular surface under the influence of gravity. Under the influence of gravity. Are obviously frictional forces there. Okay. And so this is our surface, and one more assumption is this surface can be extended up to infinity in either directions, in this direction as well as in this direction, and that is shown by these dotted lines. So we have placed the ball at this particular position, right? And the ball is at rest. So the ball is at rest means it's obvious that the velocity of the ball is zero. And if we take this position to be the reference position, right, then with respect to this reference position, the displacement of the ball is also zero. Clear? So at this particular position, the ball is at rest and hence the velocity is zero and the displacement or distance equal to zero. Clear? So this position of rest is often called the zero state, zero state or equilibrium state or quiescent state. All these terms are used synonymously. So state of zero motion, state of zero motion. So this is the equilibrium state of the system. Why do we call this state as an equilibrium state? Because if you don't disturb the ball, if you don't disturb the system, right? So if you don't disturb the system, then the ball will rest in this particular position for all time t greater than equal to 0. And t equal to 0 is our reference time. You get my point? Do I have to repeat?
No, ma'am.
So that's why this position or this state of the system is called the equilibrium state of the system. Yeah. Okay, fine. Now, what we are doing now, we are applying a disturbing force on this ball. That means we are simply pushing this ball, just slightly just pushing this ball. That means we are applying a disturbing force. This is the disturbing force. This arrow is actually indicating the push on the ball from this direction. We can push the ball from this direction as well, right? So we are applying a disturbing force, and after a while, it's a small push, okay? So after a while, we actually are removing the disturbing force, isn't it? Just we are giving a small push, that means, and after that we are withdrawing the disturbing force. It's not the case that we are continuously uh, pushing on the ball. It's not the case. Just a small push and we are removing the disturbing force. What will happen? The ball will start above this equilibrium point now the ball will start a motion or exhibit a motion in this direction, then in this direction. It will overshoot this position of rest in this manner, motion of the ball. And obviously, because of the presence of friction, what will happen? The excursion will reduce in magnitude gradually, and after exhibiting this kind of damped oscillation above this reference point, finally the ball will come to rest and will be able to regain its state of equilibrium. Am I correct?
Yes, ma'am.
Right? So, obviously, how to describe the system so far stability is concerned, since the system is able to regain its initial state of motion, that means zero state of motion, or the system is able to regain its equilibrium state, right? The system is obviously stable one. This particular system is a stable one, as it can regain its own equilibrium state after removal of the disturbing force, right? Now, this system is also described in a detailed manner and in a more technical way as globally, yes, the system is described as a globally asymptotically stable one. So that means we'll have to understand the meaning of these two terms, that is what is meant by globally stable and what is meant by asymptotically stable. Okay, learn. Now let's consider another surface. So this is the surface under this condition, right? Under this consideration. So this is the surface, and again the assumptions are same. That means the ball we have placed. Suppose we assume that we have managed to place the ball at this particular position, and the ball is resting at this particular position under the influence of gravity, right? So now, if we even apply a very small amount of disturbing force and withdraw that, that means a very small push on the ball, either from this direction or from this direction, what will happen? The ball will roll down either along the surface or along the surface. And again, our the second assumption is valid. That means the surfaces can be extended up to infinity, right? So ball will go on rolling down along the surfaces. And what will happen? Or what is the conclusion? The conclusion is the ball will never be able to regain its initial position of rest, isn't it?
Yes, ma'am.
Right? So if we compare this example with the previous, or this case with a previous one, then obviously this particular system should be termed as an unstable system. Do you agree?
Yes, ma'am.
So this is an unstable system. Fine. Next, the third case. Now we are considering a surface which is like this, right? And we have placed a ball. All assumptions are same. That means frictional force is there. The ball is resting under the influence of gravity, and the surfaces can be extended up to infinity either side. So now you see we have placed the ball at this particular position and the ball is at rest. So this is the position of rest, or this is the equilibrium state of the system, where the velocity is zero and the displacement is zero. Right? Now if you give a small push, then if the maximum excursion of this ball about its equilibrium position is limited within this zone, the surface or the system will behave like the system presented in case 1. Do you agree? The ball will execute this kind of motions and finally will regain its initial zero state or initial zero state or will come to rest. Do you agree?
Yes, ma'am.
Yes, ma'am.
So within this region, yes, we have found that the system is a stable one. But if the push is pretty large, if the disturbing force is pretty large, and if the ball crosses either this point or this point, that means crosses this ridge or this ridge, then what will happen? The case will be converted or case will be similar to the case presented as case 2. So the ball will start rolling down the surface or the surface and the ball will never be able to regain its initial zero state or will not be able to regain its equilibrium state of motion. Clear?
Yes, ma'am.
So how to differentiate this third case from the first one or from the second one? The second one was straightforward unstable system, right? What is the difference between the first case and the third case? The system is stable within this limited zone, right? Hence, to differentiate between the stability aspect of the first system and the third system, we define the stability of the system as local stability. That means the system is locally stable. The system is stable within this region only, and hence the stability can be defined or described in a better manner as the system is locally stable. Whereas, let's go back to the first case. Here you see, even if you extend the surface uh, towards infinity, then also, and whatever be the magnitude of the push, the system will always be able to regain its original state or original equilibrium state, right? So we can differentiate this case from the third one as explaining the stability or describing the stability as the system is globally stable. So have you understood what is actually indicated by the term globally stable and what is indicated by the term locally stable? That means the stability or stable operation of the system is confined within a narrow region. In that case, the system will be locally stable, right? And if the stability aspect of the system is not constrained at all, then we can say that the system is globally stable. Have you understood this? Do you have any question?
Okay, ma'am.
Is it absolutely clear?
Yes, ma'am.
So we are left with asymptotic stability for that particular term. So now next we consider a horizontal surface like this. This is the surface, right? And the ball is resting at this particular position, and this is the reference position. So at this position, the velocity of the ball is 0, and the displacement, since this is the reference position, we are considering this position to be the reference position, hence the displacement is 0, right? Now, if you push the ball, what will happen? The ball will start moving, and depending on the magnitude of the push, the ball will come to rest somewhere, say at this particular point, where again the ball will come to rest. That means the velocity of the ball will be zero. The velocity of the ball will be zero, but the displacement is not zero, isn't it?
Yes, ma'am.
Okay. So that means the ball is coming to rest, but the ball will never be able to regain its initial position. Will never be able to come back to this equilibrium state, right? But the ball is at rest. Okay. So this particular under this particular situation, the system will be called, or system will be described as a stable one, but non-asymptotically stable. Non-asymptotically stable. You'll get this term somewhere in the note. So, but in this case, if you consider the local stability, or in this case, you see the system is capable enough to regain its initial equilibrium state after being perturbed, after being disturbed, right? So if a system can regain its initial equilibrium state after being perturbed, then the system is said to be asymptotically stable. So that's why this case is best described as globally asymptotically stable. This one is unstable. In this case also, if the system is locally stable, then it's asymptotically stable. It can regain its initial equilibrium state. So that's why it's described as locally asymptotically stable. Whereas the last case, here we see that the system is stable but non-asymptotically stable, and it cannot go back to this particular position or equilibrium. It cannot come back to its equilibrium state. So is it clear? Oh, yeah, it's written over here. So the system is non-asymptotically stable. Have you understood this?
Yes, ma'am.
Yes, ma'am. So now we'll discuss. Gradually, we'll associate mathematics with the notion of stability. Okay. So both we should be able to explain the stability aspect of a system physically, and then we should be able to describe the stability of a system mathematically as well, right? So concept of stability and algebraic criterion. So already I've told you that in this course we'll be considering only linear time invariant system. So we are assuming that a linear time invariant system is either in a zero state motion, that means at rest, or it's exhibiting some dynamic behavior. When it will be exhibiting some dynamic behavior, if we apply some input to the system. If some input is given to the system, then the system will exhibit some dynamic motion, right? And in this course, along with linear time invariant system, we are concerned about dynamic system. We are not concerned about static system. So what is the definition of a dynamic system? Please answer. What is the definition of a dynamic system?
Ma'am, the systems which have transient response before the steady state response, they are dynamic systems.
Dynamic system. So why do we get the transient part? Why do we get the transient part? Or rather, how do we describe describe a dynamic system mathematically? How do you describe a dynamic system mathematically?
From a differential equation.
Yes, differential equation, and from differential equation, or to be more precise, we can say that the dynamic behavior of a system is described with the help of integral differential equation, right? And for linear time invariant system, from the differential equation or the integral differential equation, we can uh, we can also describe the dynamics using transfer function, isn't it? Yes or no? The differential equations can be converted into transfer function.
Yes, ma'am. Yes, ma'am.
Okay, so so let's assume that either the system is in zero state, that in quiescent state, that means not exhibiting any dynamics, that means there is no force, no input uh, signal applied to that particular system, or if you apply an input signal to the system, we assume that the system is exhibiting its own dynamic behavior, which is denoted by C0t. So this is the dynamic behavior within this parenthesis. You see a t, that means this is function of t. So this is the output response of the system due to the action of an impressed force, that means input signal. So one force is there, that is the input signal, and because of the presence of the input signal, the system is exhibiting a dynamic behavior denoted by C0t. Now, let's assume that we have, in addition to that, we have applied a disturbing force to perturb the system. And what is the nature of the disturbing force? This is the disturbing force dt. Can you see this? dt versus t. This is the plot, right? And we have applied the force at time t is equal to minus t1, where t1 greater than 0, right? And at time t equal to 0, we have removed the disturbing force from the system, and the disturbing force is bounded, obviously bounded in nature. So this is, suppose, is the nature of the disturbing force applied to the system. Clear?
Yes, ma'am.
So now two forces are acting on the system. One is the input signal, input force, impressed force. The other one is the perturbing force or the disturbing force. So now the system response will deviate because of this disturbing force. The system response will no longer remain C0t, but it will be, there will be a second component which is CDT. What is CDT? CDT is the response of the system because of the disturbing force, right? Is it clear?
Yes, ma'am.
So the actual response of the system CT, since it's a linear system, and since it's a linear system, hence it will obey law of superposition. Hence the actual response of the system will be sum of these two components or these two responses. One is because of the impressed force, and the second one is because of the disturbing force. So CT, the actual response of the system, will be sum of C0T and CDT. That means CT will be equal to C0T plus CDT. Do you agree?
Yes, ma'am.
Yes, ma'am.
Okay. Now we'll try to find out what is happening to CT as time t tends to infinity. That means limit time t tends to infinity, C0T plus CDT, what will be the nature of this response? So it's clear, you see that from this expression, it's clear that if as time t increases towards infinity, if CDT eventually becomes 0, then the actual response of the system will be same as the unperturbed response of the system, isn't it? Again, I'm repeating, if CDT tends to 0 as t increases, so this component will remain C0T. That means the actual response of the system will be same as the response of the system before it gets perturbed.
Yes, ma'am. Yes.
And that is basically the Desert situation, isn't it? Already we have said that for a system to be stable, slight changes, any form of slight changes, changes in initial condition, parameters, or because of the disturbing force. Just think of the example, that is the ball and surface example, where we have applied a disturbing force and then we have removed the disturbing force from the system, and the system did attain its state of equilibrium, and hence we classify the system as a stable system, right? So what is Desert? The Desert factor is the CDT should, as t tends to infinity, CDT should be equal to 0. So the actual response of the system should be same as the previous one. So for your clear understanding, this is the disturbing force that we have already discussed. And for this disturbing force dt, the response is CDT. The disturbing force acts for a finite length of time, minus t1 to 0, and vanishes at time t equal to 0. So to judge the stability of the system, or to establish the notion of the stability of a linear time invariant system, we raise this question, that is, would the system ultimately come back to its initial condition of motion, denoted by C0T, after removal of the disturbing force? That is our question, right? And we'll try to answer this question. What is the question? Again, I'm repeating, would the system ultimately come back to its initial condition of motion C0T after removal of the disturbance force or disturbing force? And we'll try to answer this particular question. And if you can find the suitable answer for this question, the answer to this question, or the actually is the basic notion behind the stability concept. So Let us assume that CT is the resulting system response due to both the impressed and disturbing forces, right? So we shall examine how the system behaves as time tends to infinity, that is, t tends to infinity. So we have posed the question with the help of the simple mathematics. So from this, it's also clear that actually we are trying to find out the nature of this term CDT as t tends to infinity. So what will be the nature of this term CDT, limit t tends to infinity, and CDT is equal to limit t tends to infinity CT minus C0t, CT minus C0t. Till now, we don't have the answer. We have not tried to answer this question. So far, is this clear?
Yes.
Okay. Since today is the first class, so or answers to this particular question in the next class. Meanwhile, I'll send you the material. Please go through these pages which we have tried to learn in this particular class, and if you find any difficulty, you can post it in the group, or you can ask me in the next class as well. So far today's class is concerned, do you have any query? Do you have any doubt?
No, ma'am.
No, ma'am.
So in that case, should I end this session? Should I stop presenting?
Okay.
Okay, Lulu.